Okay, so there's lots of different kinds of examples, and the better you or the more that you practice, the more that you go through and go through each example, the better you're going to get at this. But there's one more piece that we need to make sure we know how to do, and that's how do you check if your graph crosses the oblique asymptote? And remember, we said to check a horizontal asymptote by setting the equation equal to that constant, whatever that asymptote was. So if for an oblique asymptote, you don't have to do the whole equation. Here's the really nice part. All you have to do is set the remainder of that long division equal to 0. So all you have to do is set, I want to go a little bit thinner, set the remainder from long division equal to 0. And that's it. Set the remainder from long division equal to 0. Because if you have a remainder that you could calculate to be equal to 0, that means it divides evenly. In other words, they would have exactly that same cross point. So you set the remainder from long division equal to 0. It's called the cross point, right? And I mean, there's nothing fancy with that, just where it crosses. So if you go back up to like a couple of them we did already, for example, let's go to B. So here's example B, and I did my long division. I got this. Remember, this is the oblique asymptote. But then this was my remainder, this 59x plus 19. So if you set 59x plus 19 equal to 0 and solve, you'll find the cross point. And it's not a super nice cross point, right? Subtract 19, so you get 59x equals negative 19, and then divide by 59. So you end up getting x is equal to negative 19 over 59. Now that's just the x coordinate. That's not the y. But since this rational function and the oblique asymptote have the same intersection point, then you can put in this x value into either one. And might I suggest this one, much easier. So to get the y component of the cross point, you could say 3 times negative 19 over 59 minus 14. And whatever that equaled would be your y value for that cross point. Okay? Let's do another one, like coming down here. That one didn't have an oblique asymptote because the degree was too high. This one is the one I made a mistake on. But once I corrected it, remember this is the oblique asymptote. Here's your remainder. So we set that remainder equal to 0 and solve. So then we can add the 2, so we get 43x equals 2, which means x is equal to 2 over 43. And again, it's not the nicest of numbers, and most likely it won't be the nicest of numbers because the functions have very interesting behavior, these rational functions, but they get to the y component of the cross point. So remember, this is our cross point. Where does it cross the oblique asymptote? To get the y value, you could put it into either equation, but again, might I suggest putting it here. So the y component would be 3 times 2 over 43 minus 9, or that's like 6 over 43 minus 9. And then again, you find out what that value is, and that would be your y component. Now, it doesn't have to always cross the oblique asymptote. And the thing is, if you take a look at example A, you still kind of go through that same process. Like here's the oblique asymptote, like y equals x minus 6. Here's the remainder. So set 30 equal to, because that's the remainder, 0 and solve. Well, when does 30, that's really messy, equal 0? Never, right? No solutions. So if you get an equation that's impossible to solve, then there's no cross point, right? There's no time where those two equations are the same. Okay, so that's how you tell if the oblique asymptote gets crossed by the function. Now, I also want to do in this video, let's go through one more example together. And I want to do one that actually has, an oblique asymptote. And I think the one that I want to start with might be, well, actually, that's fine. Let's go ahead and let's do this one right here, like part C. Let's actually look at that question. Now, I know that there's an oblique asymptote because I know, the degree is exactly 1 higher. So if I do long division, just real quick, x plus 1 divide into 2x squared minus 3x. So x goes into 2x squared, 2x times 2x times 2x, 2 times x is 2x squared plus 2x. I almost did the same mistake last time. Terrible. Subtract. So 2 minus 2 goes to 0. Negative 3 minus 2 is negative 5x. And then we go, right, one more time, because there's really technically a 0, so we could bring that down, plus 0. And then x goes into negative 5x negative 5 times. So that's negative 5x minus 5. So then we subtract one more, and then we get 0. 0 minus negative 5 is positive 5. So this is our remainder. So if we want to do a quick check, does it cross? So check when does 5 equal 0? We always set the remainder equal to 0. Well, guess what? It never does. So the fact that 5 doesn't equal 0 tells me that there's no cross point. Doesn't cross the asymptote. Okay. So this is my oblique asymptote. And then perhaps you also realize that there's a vertical asymptote at x equals negative 1. So let's go ahead and sketch that and see kind of what we have. So here's my y-axis. And here's my x. And I know we said there's a vertical asymptote at negative 1. I guess maybe I'll use red. I don't know. I've been using red before, so might as well stick with the program. Oh, that's frustrating. There we go. Red. Okay, so that's x equals negative 1 as our vertical asymptote to start. And then we can graph this. Y equals 2x minus 5. So an intercept of 5, 2, 3, 4, 5, and up 2 over 1. So intercept of 5, up 2 over 1, up 2 over 1, up 2 over 1. So I've got this slant asymptote, or this oblique asymptote, going through the graph that way. And I might extend it this way. Okay, so, and again, this is y equals 2x minus 5. Let's talk about x-intercepts, y-intercepts, because if I let x be 0, I can know what the y-intercept is, which is actually really nice. When x is 0, that's 0, 0 over 1. The y value is 0. So this has an intercept of 0 for both x and y, which is really nice. But then there's another x-intercept. If I think about this, when does that equal 0? Right? When does 2x squared minus 3x equal 0? Well, if I factor out an x, I get 2x minus 3 equals 0. Once when x is 0, which we found, but also when 2x minus 3 equals 0, which means x is 3 over 2, or 1.5. So there's another intercept at 1.5. Okay, now we cannot cross a vertical asymptote. We already proved we're not crossing the oblique asymptote, and we know we've got to go through these two points. So that really dictates the behavior to the right of that asymptote. So thinking about to the right here, if I think about what's the behavior, for some reason my highlighter doesn't work very well. What's the behavior to the right? It has to be sort of trapped in that triangle because I can't cross the oblique asymptote, and I've got to go through those 2 points. So that forces my graph, I erase the highlight, there you go. That forces my graph, I liked that green pen, there you go, to come down, and then you just kind of go through and right on out, kind of like a boomerang. Now, because the asymptote x equals 1 has odd multiplicity, and I ended at positive, I must begin at the negative. And we sort of are in this boomerang down here. And so we get these two almost looking like parabolas, or almost like a hyperbola, if you know those functions. And I know that it can't be anywhere in this region, because if it were in this region, it'd have to cross the x-axis one more time. And I know it doesn't. So we just get those two branches, one that's bound in between the asymptotes kind of in the upper quadrant, and one that's bound in the lower quadrant. And again, it's just a sketch, but we know the behavior of this function pretty well, simply because we drew in those asymptotes. Okay, so pause the video, let you kind of think about that example, and we'll go through another one together. Because again, the more practice that you have going through this, the better you will be at these equations.